Hi, chemistry. I want to talk to you about net ionic equations today. And this isn't really something that's new to us. We're going to look at equations that we're already familiar with, but it's a new way of seeing the equations. And the reason I want to run you through this is because sometimes you might want to write an equation as a net ionic equation. And sometimes you'll see equations as net ionic equations, and I want to help you understand what you're looking at. So, writing something as a net ionic equation is it centralizes around this idea of aqueous solutions. So we've talked about the states of matter before, solid, liquid, and gas, and we talk about how sometimes you'll see those states represented in reactions behind the molecule that they're describing, right? And then we've talked about how there's this fourth state that is aqueous. So what aqueous means is that the ions, the ionic compounds, they dissolve in water. And when this happens, the ions will detach from the ionic lattice. They will be stabilized by the water, and the ions will actually move freely around in that solution. And those ions don't really affect each other anymore. So when we write things in an equation, like we have been doing in a skeleton equation or a balanced chemical equation, we're actually kind of misrepresenting what's there. And you can see a good example on the board here. I have calcium chloride reacting with sodium carbonate, right? And this may be true initially. Maybe I take the bottle of calcium chloride, I scoop out some of the powder, but as soon as I mix it with water, it's really not a lattice anymore, even though I have the formula written in the reaction as if it were a lattice, right? Once I dissolve it into water and it becomes an aqueous solution, these ions actually separate from each other and move around separately. And so the way we're writing it in this formula is not super accurate. And that's where a net ionic equation comes in. A net ionic equation actually writes these ions as they exist in their solutions. So I'm going to show you how to write a net ionic equation, but first, I want to show you this little animation about ionic compounds so you can see this process of dissolving that I'm talking about. All right, so thank you, Fuse School, for this animation. We're just going to watch part of it here. Let me move the drawing tools. Okay. So ionic compounds, some of them are soluble in water. And when it's soluble in water, what happens is these ions actually dissociate. So you can see the ionic lattice here. When it comes into water, these ions break off of the lattice. And you can see the sodium is purple, the chloride is green. Now, this happens because water is polar. Remember, we talked about how oxygen has this partially negative side. Well, it actually stabilizes the positive ions, and the partially positive negatives stabilize the chlorine ions. Solvation, or dissolving things, stabilize these ions. So it'll mix in water here. Let me go back just a little bit. These ions will break off from that lattice, separate, and move around the solution separate from one another because they are stabilized by these polar or partially charged ends of the water molecule. Okay, so that's what's going on. And so a better way to write the things that actually exist in the solution would be to separate these ions, to write it as the calcium ion, our two chloride ions, our two sodium ions, and our carbonate ion. Okay, now we've seen this reaction before. We've seen calcium chloride react with sodium carbonate. So I want to show you this reaction again, just to remind you of what this looks like when it happens. Do you remember what happens when we mix a solution of calcium chloride with a solution of sodium carbonate? Let's find out. Okay, so on this balance, oh, again, let me move the tools here. Okay, on this balance, you can see they actually, it's kind of cool. They show you the mass here, 77.3 grams of the two solutions together. One of these solutions is calcium chloride. The other is sodium carbonate. When you mix them together, you form a precipitate. And fun little detail, the mass is the same. You haven't created mass, you haven't destroyed mass. The ions are in both cups already, right? But when you mix them together, the ions rearrange and reform, and two of the ions will stick together and form a solid. Do you remember what that solid is? Let's write our products out and see if we can remember what that solid is. So this would be a good time to pause the video, see if you can write the things that form in this double replacement reaction, and see if you remember which one is that white solid that forms. Okay, so sodium is going to react with chlorine, NaCl. Calcium is going to react with carbonate, CaCO3. And we can go through and balance this whole equation. Okay, so do you remember what that white solid is, if it's sodium chloride or calcium carbonate? And when we did this together, we talked about how that white solid is chalk, which is calcium carbonate. So this actually forms a new solid. It's not aqueous. Those ions do stick together and form a solid in there. Sodium chloride remains as aqueous. So for our net ionic equation, where we want to represent the ions as they actually exist, we're going to write sodium and chloride separately because they will be floating around the solution. They are aqueous, stabilized by that water molecule. And we're going to keep calcium carbonate together because those ions are actually sticking together, forming a solid. So this is part of it. Notice that I have split anything that is aqueous. Anything that is solid, liquid, or gas, you do not split. Notice anything that's aqueous, I have split into the ions that make it up. And anything that's solid, I have kept together as a solid. So what we can see here is how things actually exist. The other thing we can see is what actually changes. So take a look here. Calcium starts on one side as an ion, but ends on the other side in a compound. Calcium changes. That's a chemical change. Chlorine starts as an ion on one side and it ends as an ion on the other side. Chlorine doesn't change. Chlorine is not involved in the chemical reaction. It's floating around in the beginning, it's floating around in the end, it is not changed. So anything that's not changed, we call a spectator ion. And just like a spectator of an athletic event that's not involved in the game, same thing here, the spectator ions are not involved in the chemical reaction. So that's what this term net means. What I have written here is actually a complete ionic equation. For a net ionic equation, I only want to involve the ions that are actually changing. So any spectator ion, I'm going to ignore. Can you find a second spectator ion? This would be a good time to pause and see if you can find a spectator ion. And the answer is sodium. Sodium is your other spectator. It's an ion on one side, it's an ion on the other side. So I'm going to remove the spectator ions and write what I'm left with. Calcium ion carbonate ion goes to calcium carbonate solid. So these two are still aqueous as reactants, and then once that reaction happens, they form a solid. So this is my net ionic equation. I have only included ions that change. So to write a net ionic equation, you have to start with your normal chemical equation, split anything that's aqueous, do not split anything that's a solid, liquid, or gas, and then you eliminate anything that is the exact same on both sides, and you write what's left. And what's left is your net ionic equation. So you may see these, and now you will know what you're looking at. You may want to write these. Sometimes you only want to include what's involved in the chemical reaction, the chemical change. And now you know how to do it. So let me know what questions you have on this, and I will see you in class.